Here's problem 922. A 6 kilogram object initially at rest in free space explodes into 3 segments of equal mass. 2 of these segments are observed to be moving with equal speeds of 20 meters per second with an angle of 60 degrees between their directions of motion. How much kinetic energy is released in this explosion? Okay, so what we have is a 6 kilogram object. It's going to explode into 3 equal masses. So let's imagine that it's actually 3 equal masses to begin with. And they all are stationary. So this is the way things look like initially. Total momentum of 0 in any direction we choose. That's the way it looks like initially, and that momentum should be conserved after the explosion. In other words, any direction we choose after the explosion, the momentum should add up to 0. Alright, after the explosion, we're going to have 2 of them flying off at a 60-degree angle between them at 20 meters per second. It really makes the problem easier if we can try to find some kind of symmetry with this explosion. So let's do this. Let's have these 2 particles flying off at the 60-degree angle with a relative. Let's have them fly off with the x-axis between them. So here's a 30-degree angle to the x-axis and a 30-degree angle. So here's mass 1 moving with a velocity of 20 meters per second this way, and here's mass 2 moving with a velocity of 20 meters per second this way. 60-degree angle between the 2 of them, and if I choose this way, equal masses and symmetry with their velocities, that means in regards to these 2 masses here, there will be no net momentum in the y direction because they each have equal and opposite momenta with respect to the y direction. Hence I know that my third mass is going to be going off totally in the negative x direction because there won't be any xy component to its momentum. So that's my m3 moving some velocity v3. So this might be the way that the explosion looks. And this is the way things look like finally. Alright, so if I look at this, the summation of all the momenta in any direction I choose is actually going to be 0. So I can choose any direction and figure this out. If I look at the y direction, I have that initially we have 0 momentum. Afterwards we have mass 1, velocity 1 final in the y direction, plus mass 2, velocity 2 final in the y direction, plus mass 3, velocity 3 final in the y direction. Mass 3 has no final velocity in the y direction, so this last term would be 0. And it would be true that mass 1, velocity 1 final in the y direction would equal a negative of mass 2, velocity 2 final in the y direction. Mass 1 and mass 2 being equal, we can divide those through, and we have that v1 final in the y direction is equal to negative v2 final in the y direction. In other words, v2 final in the y direction is going to be a negative v2 sine 30 degrees. So we have v1 sine 30 degrees is equal to a negative v2 sine 30 degrees. Makes sense? Sine 30 degrees cancel out. Negative cancels out. And we basically have, at least in terms of velocities, that v1 equals v2, which is what we were given. So the fact that our net momentum in the y direction is 0 pans out. We probably didn't even have to prove this. Let's look at the x direction though. In the x direction, we have that zero momentum to begin with, mass 1, velocity 1 final in the x direction, if I can get this to right, plus mass 2, velocity 2 final in the x direction, plus mass 3, velocity 3 final in the x direction. So we have 0 is equal to mass. They're all the same masses, so let's just use m. Velocity 1 final in the x direction is equal to v1 times the cosine of 30 degrees. It's positive. Mass 2 is m. v2 final in the x direction is v2 cosine 30 degrees. It's positive. And then I have mass 3 is also mass m. And then I have v3 final in the x direction, which is actually just going to be v3. Divide through by m and bring v3 over to the other side, and we basically would have that v3 final in the x direction, which is equal to v3 because v3 is totally in the x direction, is going to equal a negative v1 cosine 30 degrees plus a negative v2 cosine 30 degrees. v1 and v2 are the same, so this is actually going to equal a negative 2 times v, which is 20, times the cosine of 30 degrees. So it's going to be a negative 40 cosine 30 degrees. What is that? A negative 34.64 meters per second. That is v3 final, and that is v3. So that is the velocity of mass 3. Now with this final velocity, we can find the kinetic energy of the system after the collision, or after the explosion. So here's our pure kinetic energies after the explosion. Our final kinetic energy is going to equal 1/2 mass 1 v1 final squared plus 1/2 mass 2 v2 final squared plus 1/2 mass 3 v3 final squared. So this is going to be 1/2 times 2 kilograms times 20 meters per second squared plus 1/2 times 2 kilograms times 20 meters per second squared plus 1/2 times 2 kilograms times 34.6 meters per second squared. It's hard to fit in there. One half and the 2's cancel. And so we end up with 20 squared plus 20 squared plus 34.64 squared. That's going to be 400 plus 400 plus 1200, which will give us 2,000 joules. So that's our answer. The final kinetic energy of the system after the explosion is 2,000 joules, and that's the energy released in this explosion. 2,000 joules.